Consider two spheres. One is a tiny bead, the size of a marble. The other is a massive sphere, perhaps the size of a planet. Now, imagine we drill a straight, cylindrical hole directly through the center of both spheres. Here is the constraint. We stop drilling only when the remaining band, the napkin ring, has this specific height, h. Now look at them. The planet ring is incredibly wide, but very thin. The marble ring is thick, but small. Intuition screams that the massive planet ring must contain more volume. But geometry offers a shocking conclusion. If the height h is the same, the volume of material in both rings is exactly equal. This is the napkin ring paradox, a problem where intuition fails and geometry reveals a glitch in the matrix. Let's break down the geometry. We start with a solid sphere with a radius we will call big R. Next, we cut out a cylinder from the very center. This cylinder has a radius we'll call little r. What's left is a spherical band. In geometry, the only parameter we care about for this paradox is the height of this band, h. Notice the geometric trade-off. A small radius creates a thick, chunky band, but a massive radius results in a razor-thin strip. Yet the vertical height, h, is identical in both cases. We could try to solve this the hard way, using brute force calculus. We set up the integral for a volume of revolution, subtracting the cylinder from the sphere. It looks messy. But remember our geometric constraint, the relationship between the inner radius, little r, the outer radius, big R, and the height. Now, watch what happens when we substitute that constraint into our integral. The terms involving the large radius, big R, appear twice with opposite signs. They cancel each other out perfectly. The variable for the sphere's size has vanished. We are left with a clean formula that depends only on the height, h. This proves mathematically that the size of the original sphere is irrelevant. But there is a more elegant way to prove this, without messy integrals. Enter Cavalieri's principle. Imagine a stack of coins. If you slide them around, the shape changes, but the volume stays the same. Why? Because every individual slice still has the same area. Let's apply this. We will compare our napkin ring on the left to a standard sphere on the right that has the same diameter h. We will slice both objects at some arbitrary height z from the center. Now for the magic algebra. The slice of the napkin ring is a washer, a big circle minus a small circle. The slice of the sphere is just a disk. Using Pythagorean relations, the areas match perfectly. Since every slice is identical at every height, Cavalieri's principle tells us the total volumes must be identical. If you still don't believe it, take this to the logical extreme. What happens if we shrink the inner hole to 0? As the hole vanishes, the napkin ring simply becomes a solid sphere with diameter h. The volume equation holds true all the way down. This is why the volume is constant. All valid napkin rings, no matter how big the original sphere, share the exact same volume as this tiny bead. For those who want to see the full algebra, here is the complete derivation step by step. First, we start with the volume of the original solid sphere with radius big R. Next, we calculate the volume of the drilled cylinder. This is simply the area of the hole times the total height. We must also account for the two spherical caps at the top and bottom, which are removed during drilling. The volume of the napkin ring is the sphere minus the cylinder minus the caps. When you expand these terms and apply the Pythagorean theorem, every single R term cancels out. We are left with this beautiful result. So next time you see a napkin ring, remember the paradox. It doesn't matter if it fits around a finger or a galaxy. If the height is the same, the volume is exactly the same. The radius of the sphere simply cancels out. But before you go, I have a challenge for you. What if we drilled a square hole instead? If we maintain the same height constraint, does the volume still stay constant regardless of the sphere's size? Let me know what you think in the comments. Math is full of beautiful surprises like this. I am creating a whole series of visual paradoxes here on Luminous Math. If you want to catch the next episode, don't forget to subscribe.